Now that we have an idea of strong acids and weak acids, we can get specific about the strength of an acid. So the strength of an acid is going to depend on its ability to donate a proton. And its ability to donate a proton is going to depend on the strength of the bond that is attached to the acidic proton itself, okay? So we can layer information here and apply knowledge of atomic trends like atomic radius and bond properties like bond length and bond energy to determine the trends in acid strengths, specifically for nonmetal hydrides, oxoacids, and hydrated metal ion. And that all of these particular species are going to contribute to acidity in some way. And so this is how we're able to understand it. First up is going to be the nonmetal hydride. And so nonmetal means we're dealing with a nonmetal, and a hydride means it's definitely going to be attached to a hydrogen. And there are going to be two factors that determine how easily a proton is released when you have a nonmetal hydride. And the first factor is going to be electronegativity. So EN is going to stand for electronegativity. And then next is going to be the strength of that nonmetal hydrogen bond. So whatever the nonmetal, that a bond to that acidic proton is going to be very important and help us figure out the strength of a nonmetal hydride. Let's focus on electronegativity first. So electronegativity is going to increase as you go across a period, right? Well, the same thing when it comes to acid strength. If you increase electronegativity as you go across a period, you're also going to increase acidity as you go across a period. Another way you think of it is that you can increase acid strength as you go across a period. So that's one factor that's going to help us. The next factor that we layer on is going to be the strength of that nonmetal hydrogen bond. And so bond strength is one property we can think of that's going to decrease as we go from the top or down a group, from the top to the bottom or down a group on the periodic table. We're going to have bond strength that's decreasing. We also have a situation where the bond length is increasing. So when we go down a group, we're going to have a nonmetal. It's going to have a very long bond with the proton here. And so because I have a very long bond, that means it's going to be easier for this proton to be removed. Okay, that means you're going to increase acid strength if you have that ability. Also, bond strength. Because the bond strength is longer, and so the bond strength is going to be weaker, that means it's going to also be easier to give up a proton when you're dealing with length and strength, okay? Versus if you have a nonmetal attached to the hydrogen proton and it's very, very short, that means you're going to have an increase in bond strength, and it's going to be harder to give up this overall proton. And so you'll see the acidity or the acid strength decrease in that situation. An example of a nonmetal hydride would be H2TE Hawkeye, okay? So as you can see, you have two ionizable protons here. That means you have a hydrogen and a nonmetal, which is tellurium. And so H2E is definitely going to be a nonmetal hydride here. So if it's going to be a nonmetal hydride, it's going to be contributing to acidity. We have to think of the ability for H2TE Hawkeye to give up one of these protons here. And yes, it is diprotic, but we're only going to focus on the first proton that is released. So I always think of it as, okay, Hawkeye has the ability to have very high precision with projectiles. So I can think that he has an arrow. He's going to have a projectile that is going to symbolize a proton being donated, right? Now, depending on how far that projectile goes, that's going to tell you how strong of an acid it is. With H2E tellurium, it actually has a very, very long bond length. And so it ends up being a strong acid here. So H2TE Hawkeye is going to represent a strong acid, strong Bronsted-Lowry acid, and also a non-metal hydride. We can then layer these two trends, electronegativity and strength of the non-metal hydrogen bond, to bring it together to help us really know and assess the strength of all these different weak and strong acids. So before we saw like HCl HOPE, for example, we know that they're part of strong acids. HBr is a strong acid, HI is a strong acid. And we told ourselves, okay, these halogens are a strong acid, but HF is a weak acid. So now we get to use and layer the information to kind of figure out why. Yes, HF has a high electronegativity, but it's very, very high up on the periodic table as far as groups. So it doesn't fulfill really the long bond length or the higher bond energy here. So that's the reason why HCl, HBr, and HI are all considered strong acids, where HF is considered a weak acid. And you see here, it just says Ka1, or it doesn't say a Ka value for these strong acids here. So for us to be able to distinguish between strong acids, we have to add another layer of information, which we'll see as we go along in the next part of this chapter. Next up is going to be the acid strength of oxoacids. So an oxoacid is going to have a hydrogen and it's going to have a amount of an oxygen atom, right? And so with acid strength of oxoacid is still going to depend on two factors. The first is going to be the electronegativity of the central nonmetal. So of course, as we go across a period, that's going to increase acid strength, just like we saw before with the nonmetal acid hydrides, right? Then it's also going to be based on the number of oxygen atoms. So if you increase oxygen atoms, you're going to then increase acid strength. Okay, let's look at some examples here. So we have HOI, HOBr, and HOCl. Because in the first factor, electronegativity is going to increase the oxoacid strength, that means HOI is going to be less than HOBr, and HOCl is going to be our highest as far as acidity goes because it is the most electronegative. Now our next portion, the number of oxygen atom increases and so does acidity. So we have some examples here. HOCl is going to be less in acid strength than HOClO because now we've increased the oxygens by 2 here. And if we increase the oxygens by 3, it's even more acidic. And if we have an oxygen here which has 4, it's the most acidic. Okay, folks? So we can use that to help us understand the acid strength of oxoacid. Of course, we do have acetic acid, Dr. Strange, which we've seen before, or CH3COOH. There's only going to be 2 oxygens here to help relay what the strength of this particular oxoacid is. Again, because Dr. Strange is going to be a weak acid here, he does have the ability to give up a proton, but again, he's going to be able to keep everything close to the chest because since he alters reality, it takes a lot to actually be able to do that. And there's a time limit on that. So most of the time, you're going to see acetic acid, Dr. Strange, and the CH3COOH or protonated form. And finally, the hydrated metal ion. Hydrated means that they're going to be surrounded by water. And then metal ion means that you're usually dealing with a small metal, okay, that's highly charged. And so what it means by highly charged is that we're usually thinking of something that is going to be higher up on a group, right? So it must be really, really small. And it usually has a charge of 3+, 2+, 4+, anything that's a little bit higher than 1, for example. Okay, folks? So an example of a hydrated metal ion will be the metal raised to that charged amount that you're then going to mix with water. Once you mix it with water, it's going to form the complex ion that you see here. And this complex ion is surrounded by water molecules. And then that's going to be raised to a charge, okay? The next thing we do with a hydrated metal ion is we take that hydrated metal ion and then we continue to mix it with water. Guess what, folks? There's going to be enough electron density from one of the water molecules here to then accept a proton from this water molecule, for example. Okay? So one of these water molecules here are going to be able to donate a proton, and therefore it's going to be able to form H2O+. What is then going to be left over? Our metal, still going to be hydrated to some waters, but you're going to be down by 1, and then you're going to have OH left over because the proton is coming from this water molecule here. Okay, folks? And so, yes, that is a lot. Do you have to memorize each of these? No. Let's get into an example. And the example I'm bringing up is our first villain, which is going to be FeH2O6 3+ Mysterio. Okay? I love Mysterio. He's always cool to me. And I love that he has a lot of illusions and he can manipulate people that way. So in my head, when I start thinking of hydrated metal ions, I'm like, okay, Mysterio is that iron metal, and his illusion is that he has all these water molecules that he's using to manipulate anything around him. And then at any moment, one of those water molecules can end up donating a proton because of the lone pairs that are on the water that is existing around it. Okay? And so the illusion effectively stops once we're able to donate that proton to the water in this second step. So that's kind of how I thought about using FeH2O6 3+ Mysterio for this example. Another way to illustrate this would be when you have aluminum H2O6 3+ here. As you can see, we have all of our water molecules in an octahedral pattern. You have the water that's also mixed in, and that water molecule is going to be able to form H2O+. And what's left over is that you're down 1 water molecule and you're left with OH 2+ here. And so you're effectively creating a brand new complex ion in this area. What I want to do is just show you what these reactions look like for Mysterio. Okay, so we're starting off with iron nitrate or iron 3 nitrate. We're going to mix with water so that we can form our complex ion of hydrated iron 3+, right? Then we're going to take our hydrated iron 3+ complex ion, mix it again with water, and this is when we form our new complex ion, which is FeH2O5 OH 2+. And what else do we form? H3O+. So the fact that we're able to form that H2O+ is the reason why hydrated metal ions are considered acidic. We also saw oxoacids that are acidic, and of course our non-metal hydrates that are acidic. At this point, we're able to cover majority of all of the types of acids that we see in this course. Now let's move on to bases, and weak bases specifically.